Alrighty guys, so for today, we're going to be talking about 5.1, and that is finding the distance using integration. Now, the simplest way to do this is if you just have a function or a graph, and so you have the function here, and you have your boundaries from A to B, and then your distance or your displacement is going to be the area underneath that curve. And with your for your y-axis, that'll be v of t, and for your x-axis, that's just going to be t. Now, if you were to have a function using integrals, let's just say a is equal to 9.8 meters per second squared, and that is the gravitational acceleration constant, and taking the integral of a is equal to a t plus c. And c is going to be our initial velocity. And then if you take the integral again of a t plus vi, that's going to be equal to 1/2 a t squared plus vit plus d. And d is just going to be the initial distance before you find it. And that total thing is, that's how you're going to find your displacement for the function. So 1/2 a t squared plus vit plus di is going to equal to your total displacement for the function between an interval of t. Now, a common mistake that people make is they get displacement and distance mixed up. So let's just give an example here. Let's just say between points A and B, and over the interval of t, let's just say you started out at the beginning of the interval A, and let's just say after 10 seconds have passed, you're at B. So that's just drawing a line between the 2 points, and that's how you find your displacement. But if you were to actually look at what happened, it's possible that this person actually went from A to B, and they went from here, and then they went back, and then they went back again. So they still ended up in the same place. They still ended up at B, but they actually ended up traveling the distance 3 times. And that's why displacement is different from distance. Now let's just do a practice problem here. And if you were to have a function, just say root 36 minus x squared. Okay, so that's obviously related to a circle. And let's just say that quadrant 1 is our boundary. So in this case, the y-axis and the x-axis are our bounds for finding the area. And for here, we know that the radius is equal to 6. So here it ends at 6 and 6. And to find the area, you're going to do 1/4 pi r squared, which is equal to 1/4 pi times 36, which is equal to 9 pi. And that will be your displacement for this function. And then another very common way is if you were to have a table of values. So let's just say here's time and here's velocity, and let's have our intervals of time be 5 seconds. So we start at 0, 5, 10, 15, and then 20. And then we have the velocity at each of these intervals. So at time 0, we have 10, and then 17, 24, 13, and 30. And if we were to draw this out, we would get spikes in the graph because it's not a continuous function. And so the easiest way, or the most accurate way to find the displacement is to take L4, R4, and M4. And that is drawing different rectangles in the function, and we're finding it from the left boundaries, from the right boundaries, and from the midpoint. Or actually, let's just make this M2, just to make it a little bit easier. So L4 is going to equal to, so delta x in this case is equal to 5, right? So you're going to do 5 times 10 plus 17 plus 24 plus 13. And then R4 is going to be equal to 5 times 17 plus 24 plus 13 plus 30. And you can see the difference. One of them is shifted over in the data, So R4 is going to start when velocity is equal to 17, and L4 is going to start in the beginning when time is equal to 0. And then for M2, that's going to equal to, so because it's only 2 rectangles, we're going to make delta x equal to 10. That's going to be 10 times 17 plus 13. All right, so for L4, we're going to be equal to 320 units squared, and this is going to be equal to 420 units squared, and this is going to be equal to 300 units squared. And you can tell just because it's L4 and R4 and there are only 4 rectangles, there's actually quite a bit of variation between the two. And obviously if you were to add more rectangles, it would get more and more accurate. That's why when an integral, you have an infinite amount of rectangles. And so M2, because there's only 2 rectangles, it's even more different. And then a good way to get the approximation is to get T4, which is trapezoids, and T4 is always equal to L4 plus R4 over 2, which in this case is 370. So 370 units squared is most similar to what the actual displacement is going to be. And that is going to be how you find distance in chapter 5.1. Good luck, everyone.